then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great.
Tis the season to be serving.
When I was solving equations, I was feeling amazing.
Greetings, calculus students. Welcome to lesson number 6. Let's get into it. So today's lesson is about continuity, particularly continuity at a point. This is something I've been making mention of on numerous previous lessons and kept saying we'll formally cover this at a later date. Well, the date has arrived. So here's the date where we formally will take a look at continuity at a point and also types of discontinuities, which we've already kind of looked at, talking about the jump, the infinite, and the removable. But we'll look at that in a more formal fashion today. We're not going to review anything today. So today we're going to get right into continuity. So I want to begin by showing you the definition of being continuous at a point. 3 conditions must hold. And so a function f is continuous at c if the following conditions are met. And those conditions are f of c is defined, the limit as x goes to c of f of x exists, and those things must be equal. So those are the 3 conditions to be continuous at a point. So if any of those 3 things do not occur, then you're not continuous at a point. So to be continuous for the function f of x to be continuous at x equals c, f of c must exist, and the limit as x goes to c of f of x must exist, and they must be the exact same number. So all 3 of those conditions must hold for a function to be continuous at a point. And this, you can see when all this holds, when a function is continuous at a point, you see here the limit is equal to f of c. And so those are the type of problems where we can just plug the number in and get the limit. I called those well-behaved functions previously. So a well-behaved function is continuous at that point. And when a function is continuous at the point, the limit is just the value of the function at that particular point. Okay, that's the definition of being continuous at a point. So if you're not continuous at a point, then you're discontinuous. So you have what is called a discontinuity. Okay, so we're going to look at some examples of functions which are not continuous at a given point. And we're going to explore each of our 3 conditions. So this is our first guy. And here we're talking about checking continuity at x equals -2. And if you look at x equals -2, the function is not even defined. So this is a case where f of c is not defined. So again, if f of c is not defined, you can't be continuous. So there's obviously a discontinuity here. And we want to also talk about the types of discontinuities we see. There are 3 main types. And one is if you have a function and you have its whole graph, this whole graph is looking quite nice, but one little point is missing, or there's one little hole on the graph, that is called a removable discontinuity. So whenever you see this, you see the whole graph, but at the x value that you're checking, there's a little hole or just a little point missing. That's called a removable discontinuity. So quite naturally, removable discontinuities are also called point discontinuities or holes because of the graphical representation there. Let's look at another example where f of c is not defined. And so here we will be checking the continuity at 1. And it's just like the previous example. You see at 1, the function is not defined. And again, it's just a little point missing. So again, this type of discontinuity is a removable discontinuity. Let's look at another example where f of c is not defined. So again, we're checking continuity at x equals 1. Notice open circle, open circle. So f of c is not defined, but this type of discontinuity is a jump discontinuity. And that is because you're on this part of the graph when you get to the X value we're trying to check, it jumps to another value. It can jump up or jump down, but it jumps to another value. So the whole graph jumps up. We're not just talking about a point, but the whole graph jumps up to another value. That's called a jump discontinuity. A jump discontinuity is a type of non-removable discontinuity. But from a graphical standpoint, what it looks like is quite easy to see, and we've talked about it before. The values, the function just jumps to a different value at the given X value which you're investigating. And also another example where f of c is not defined. So here we're talking about checking continuity at x equals 0. And so here on this particular graph, it gets very close to 0, but this graph is never going to touch 0. So f of 0 is undefined. But in this particular graph, you can see as you get close to 0 from the left and the right, you're either going to infinity or negative infinity. On the left, you're going to negative infinity. On the right, you're going to positive infinity. So when that occurs, you have what is called an infinite discontinuity. So we have an infinite discontinuity when the graph is going to infinity or negative infinity from the left or the right as we approach the given value that we're trying to find. An infinite discontinuity is also a vertical asymptote, and an infinite discontinuity is another type of non-removable discontinuity. But again, you should be able to easily recognize it when you see the graph shooting to negative infinity or infinity as you're going to the value in which you're checking continuity. So now let's look at cases where the limit doesn't exist. So we've investigated where f of c is not defined, and we'll also look at some cases where the limit doesn't exist, and we're going to see some of the same graphs, because on many of those graphs, not all of them, but on many of the graphs we just looked at, not only was f of c not defined, but the limit also did not exist. And so the one we just looked at is an example where the limit doesn't exist. Obviously, it's going to negative infinity on the left and positive infinity on the right. But still, when you look at this, you know this is an infinite discontinuity. And here's that jump discontinuity again. And also here, we talked about f of c not being defined, but also the limit does not exist because it's going to a different number on the left than it is from the right as x goes to 1. So the limit also doesn't exist. And again, if you see the function going to two different finite numbers from the left and the right, that's going to be an indication of a jump discontinuity. And of course, in those cases, the limit does not exist. And here's just another example of a jump discontinuity. So right here, the limit doesn't exist. So we're talking about as x is going to -1, the limit doesn't exist. And you can clearly see a jump. Now here at x is going to -1, f of -1 is defined. F of -1 is 2. So you can have a jump and f of c can be defined, but what makes it a jump is that the left-hand side limit and the right-hand side limit are going to two different values. So these guys are going to two different values, so the limit doesn't exist, and that's a jump discontinuity. And then next, we want to look at where the limit exists and f of c exists, but they're not equal. The limit exists and f of c exists, but those two guys happen not to be the same. And that would be where x equals 3 on this graph. So notice f of 3 is actually defined. F of 3 is -2. There's a closed circle right there. F of 3 is -2. And the limit actually exists. The limit of f of x as x goes to 3 is -1. The limit is -1. But the limit and f of 3 do not equal, so it can't be continuous. So this is a removable discontinuity. So again, anytime you see the point, the little point missing, that's going to be a removable discontinuity. So let me be a little more specific, because you can say at x equals -1, there's a little point missing. So when you see a little point missing, but the rest of the graph is in the same place from the left and the right. So here there's a point missing, but from the left and from the right, I'm going to -1. That makes it a removable discontinuity. And so when that little point is missing and the limit exists, and whether it's not defined somewhere else, or even if it is defined somewhere else, that's going to be a removable discontinuity. Okay, let's look at some example problems and see how we do with this stuff. All right, so we define continuity at a point. We showed you the 3 common types of discontinuities. Those are removable, jumps, and infinite discontinuities. And you should be able to look at them from a graphical standpoint and be able to identify those 3 types of discontinuities. And here, these problems here are going to be asking different things, and we're going to utilize our knowledge and try to answer these questions in the best way possible. So this first problem, it says the graph of f of x is shown above, and it says, is f of x continuous at x equals -2? So here's x equals -2 right here. So is the function continuous at x equals -2? What do you think? So you should say no. So anytime you're looking at an x value, and if you see an open circle, you're not continuous at that point. No matter if it's defined somewhere else, anytime you see an open circle, you're not going to be continuous at that particular point. So this is definitely not continuous, but why? So what is making a function not continuous? So answer choice B says f of -2 is not defined. Is that true? That's not true. F of -2 is defined. F of -2 is 2. Answer choice C says the limit as x goes to -2 of f of x does not exist. Is that true? That's not true. The limit exists. The limit is 4. You can clearly see here from the left and from the right, as x goes to -2, the function approaches 4. So f of c existed and the limit existed, but f of -2 is not equal to the limit as x goes to -2. So that's the answer to that problem. And of course, if we asked you what type of discontinuity we have right here, you would say what? Removable, correct. So the only type of discontinuity where f of c exists and the limit as x goes to c of f of x exists, but it's not continuous because they're not equal, the only time that happens is with a removable discontinuity. Let's look at our next example. And so here, the graph of f is shown. Is f continuous at -1? So here's -1 there. So is the function continuous at -1? Well, I don't know. Let's go through the checklist. Is f of -1 defined? Yeah, sure. F of -1 is 4. Is the limit as x goes to -1 of the function, does that limit exist? Yeah, that limit exists. Going from the left and from the right, it's 4. Are they equal? Absolutely, they're equal. So f of -1 is 4, and the limit was 4, so that is continuous. And that's kind of how it looks to be continuous at a point. You're not going to see an open circle or a jump or shooting to infinity or negative infinity. So you see all these points that my arrow is on, the function is continuous at all of those points. The function is not continuous at -4 because you have a jump. The function is not continuous at 2 because you have a jump. The function is not continuous at 4 because you have a whole or removable discontinuity. So again, for it not to be continuous, you have to see a hole, you have to see a jump, or you have to see the function shooting to infinity or negative infinity. So that guy was continuous at x equals -1. Our next guy. So it's the same graph. And here we're checking that x equals 4. And again, let's go through the checklist. Is f of 4 defined? No, there's no closed circle where x equals 4. So f of 4 is not defined. So that solves it. Now, of course, what this one is saying, both B and C, so also that the limit does not exist, but the limit does exist. You can see there, the limit equals 2. So it's just the fact that f of c was not defined that caused this particular issue. Let's look at our next one. So here we're checking, is it continuous at x equals 2? So here's x equals 2 here. Again, let's go through the checklist. Is f of 2 defined? Yes, absolutely. F of 2 is -1. You got a closed circle right there. F of 2 is -1. Does a limit of f of x as x goes to 2 exist? That would be a negative because it's going to -1 on the left and 5 on the right. So the limit does not exist. So that's what's causing it not to be continuous. And again, when the limit goes to 2 different finite values from the left and the right, that's an indication of a jump discontinuity. Let's look at our next one. Okay, so this one, which of the following statements are true? So we're just basically going through the checklist for -1. So first statement, f of -1 exists. What do you say? Yeah, absolutely. F of -1 is -3. Okay, so Roman numeral 1 is true. Roman numeral 2, the limit as x goes to -1 exists. What do you think about that? That would be a negative, going to 2 different numbers from the left and the right. And you should be identifying, okay, that's a jump discontinuity right there at -1. So this guy is a negative. Roman numeral 3, f of x is continuous at x equals -1. Well, no, if the limit doesn't exist, you can't be continuous. So it definitely can't be continuous. So the only guy that's true is 1. Let's look at our next problem. Now, these are very popular problems on the AP exam. So for this particular problem, it says let f be the function defined above, where k is a constant. For what values of k is f continuous at x equals 2? So I want to find a value of k, and this is a piecewise function, by the way. I want to find a value of k for it to be continuous. So let me kind of go back and look at a different graph to show you kind of what we mean on this. All right, so I'm looking at this graph, correct? And this graph is continuous at x equals 3. I think you would agree. This graph right here is continuous at x equals 3. And of course, what makes it continuous is that f of 3 exists, and f of 3 is 5, and the limit exists, and the limit is also 5. So that means that the left-hand side and the right-hand side of the function are equal. So when you have a piecewise function, what you want is those two pieces to equal the same number. If the left piece and the right piece equal different numbers, you're going to have a jump discontinuity on a piecewise function like that. So again, piecewise functions give us a lot of these jump discontinuities when one piece doesn't equal the other piece. So if I want it to be continuous, I kind of want these two to be equal. So it looks something like this. So I want, basically for this problem, I want to find the value of k that will make both of these equal. Again, this value that's less than 2 is the left side. This value that's greater than or equal to 2 is the right side. And so for it to be continuous at x equals 2, I need these pieces to be equal. So what we do is we set these equal to each other. Now, of course, we're checking continuity at x equals 2. And so we're going to plug in 2 for x. And then we're going to solve for the value of k that allows those to be equal. So let's take a look and work this out. Okay, so here is the situation here. Again, for this to be continuous, I need these pieces to be equal to each other when x is equal to 2, of course. So I'm going to find the value of k that makes that happen. So what I'm going to do is set these pieces equal to each other, and I'm also going to plug in 2 for x, because again, we're checking continuity when x equals 2. So what that gives me is 3 cosine 2 pi, and that should equal 2k minus 9. So again, I just want to find the value of k which makes these equal. So basically, I'm plugging this number in for x and solving for k. And what I've been very impressed with thus far is that many of you have already started to study those trig values, because you understand the importance of it. Because if you weren't studying those trig values, if you didn't know the trig values and you had to do this problem, there's no way you can solve it, because you wouldn't know the cosine of 2 pi. But the good news is that many of you have already started to study those trig values. So you're already starting to learn all those very important trig values. And therefore, you know that the cosine of 2 pi is simply 1. So this is going to be 3 equals 2k minus 9. And then from there, 2k minus 9. So 3, I wrote x equals 2k minus 9. Then from there, it's basic algebra. We'll add 9, that's 12. We'll divide by 2, and we'll get 6. So 2k is 12, so k is 6. And that's all you have to do on that problem. Again, for it to be continuous at x equals 2, the limit has to equal the value at the point. So this is going to be the value of the function at x equals 2 because of the or equal to sign. So I can find that value, but I need the limit to be equal. So this corresponds to the right-hand side. So I need the left-hand side to also equal that point, and that's what's going to make it continuous. So anytime you see these type of problems, and you will, they're a very common type of problem. Again, plug in the value that you're checking for x into both pieces, set both pieces equal to each other, and solve for whatever variable they want you to solve for. Okay, so that one we got 6. So that guy was 6. And let's do one more problem like that. Again, it's a very common type of problem. So again, there we go. We have this situation. That's 2 again. And so I'm checking, I want to find the value of k where f is continuous at 2. So let me write this out. So x squared minus 2x plus 10, set that equal to kx plus 3, and just plug in 2 for k and solve for x. And then just plug in 2 for x and solve for k. All right, so let's plug in 2 for x. So if I plug in 2 for x, this would be 4, and this will be minus 4, so that would be 0. So I'll just get 10. So 10 equals 2k plus 3, and then we're just going to, do the little algebra. So that's going to give us 7 over 2. So 7 is 2k, so k is 7 over 2. And that is it on that guy. So k is 7 over 2. That concludes lesson number 6, I believe it is, and we'll see you next time.
Should I go in? Okay, I'll go in. This is mathematics, let's bring the show in. It's like it's snowing, it's so cold. And when I bring the flow in, it's so bold. I give you a la mode, we give you what you want. Pre-cal, trig, calculus, cannot front.